Hi everyone, in this video we will introduce our work, task, an efficient framework for instant error tolerant spatial keyword queries on road networks. Our presentation will unfold from the following 5 sections. First, we introduce the research background. Geotextual objects associated with both geographical and textual information are ubiquitous in daily life. Instant spatial keyword queries return the results as soon as users type in some characters instead of a complete keyword. It allows users to query the geotextual data in a type-as-you-search manner. Specifically, with every character of keyword being typed in, the instant spatial keyword queries return geotextual objects that are relevant to the query inputs. The instant spatial keyword queries save users from typing incomplete keywords, and thus are helpful for users in real-world applications. As an example, assume that a user wants to go to a restaurant called Mama Seafood for dinner, and uses the location-based service to find the location. As shown in Figure 1, as soon as the user types in Ma, the queries can return the results containing Mama Seafood for her, him. However, the state-of-the-art methods of instant spatial keyword queries suffer from several limitations. First, the existing methods are mainly designed for the Euclidean space. All those techniques cannot be applied to road networks since they use different metrics to compute the distance between two objects. Secondly, the existing methods do not consider the typographical errors of input keywords. Sometimes, typing accurately is a tedious task, and the user's inputs tend to contain typographical errors, especially for mobile devices. Third, the traditional instant spatial keyword queries mostly focus on the cases where users type in queries character by character. They do not consider cases like deleting characters from the tail and add, delete characters anywhere in the query. Therefore, in this work, we study the problem of instant error tolerant spatial keyword queries on road networks. Our contributions are as follows. First, we identify and formalize the problem of instant error tolerant spatial keyword queries on road networks. Second, we design a novel index called R2T, which seamlessly integrates the spatial and textual information. Third, we present efficient algorithms to answer queries using R2T. Finally, we conduct extensive experiments on real-world road networks. Next, we give some definitions from the paper. First, the edit distance and prefix edit distance. Given a keyword and two strings, the edit distance between these strings is the minimum number of single character edit operations needed to transform str1 to str2, including insertion, deletion, and substitution. The prefix edit distance between strings is the minimum edit distance between prefix of a string and another string. For example, the edit distance of school and scholar is 3. The prefix edit distance of school and sco is 1. The edit distance of sch and sco is 1. Then, we propose a new query type called error-tolerant spatial keyword queries on road networks. Given a road network, a parameter, an error threshold, a query which contains a query location and query string, the error-tolerant spatial keyword queries on road networks return a set or such that the number of results in R is k. Each vertex in R has at least one keyword whose prefix edit distance with a query string is less than to. The vertices in R have the smallest scores. The score is calculated as follows, which combines and normalizes the spatial and textual similarities. So the problem we study is as follows. Given a road network and some parameters, and a query, the problem of instant error tolerant spatial keyword queries on road networks should return the set or satisfying the 3 conditions in definition 2, and update or whenever the query string changes. To solve the problem, we propose an efficient framework, termed as task. Task consists of an index component, a query component, and an update component. The index component is responsible for constructing the R2T index for the road network, and maintaining R2T when the road network changes. Task uses the query component to return results to the user. Whenever the user makes change for the query string, task calls the update component, which employs the information of previous query processing to quickly update the results for user. The user proceeds to type in the query string until the desirable results are found. We propose a novel index called reverse 2-hop label-based tree. R2T integrates both road network information and textual information. Specifically, we employ the reverse 2-hop label and tree techniques to store spatial and textual information, respectively. we first introduce the two-hop label technology. Given a road network, the two-hop labeling of each vertex is LV, which containing a set of pairs. The two-hop labels of all vertices have the following property. The distance between any two vertices can be computed via an intermediate hop. We design reverse two-hop label inspired by the two-hop label. The reverse two-hop label of a vertex consists of pairs. If a vertex V is included in the two-hop label of U, the reverse two-hop label of V contains U. The two-hop label only supports distance computation between two vertices. Given two-hop labels of a road network, if we want to find the k nearest neighbors of a vertex V, we should compute the common two-hop label vertices of EV and every other vertex, which is time-consuming. With the help of reverse two-hop label, we only need to compute the common two-hop label vertices of V and versus k nearest neighbors, and thus improving the query efficiency. The following figure shows a road network and the corresponding labels. Then, we introduce the reverse two-hop label base tree. A or 2T of a vertex consists of the reverse two-hop label of V and the tree of V. The figure is the tree of all keywords in the road network. However, storing the entire T, V, directly in R2T, V, has two drawbacks. There is some spatial redundancy in R2T, and the tree of each vertex is part of the complete prefix tree, so we only need to save the complete prefix tree repeated tree traversal. Multiple tries need to be accessed. To address these issues, we use a node array to store ID n as the ID of n in the complete tree of the road network, and Bn consists of bitmaps of tree nodes along the path from root node to n. To address these issues, we use a node array to store ID n as the ID of n in the complete tree of the road network, and Bn consists of bitmaps of tree nodes along the path from root node to n. Note that the bitmaps of root node, leaf nodes, and the nodes whose bitmaps are the same as leaf nodes are not stored. A bit is set to 1 if the represented vertex has a keyword containing the prefix denoted by n, and it is set to 0 otherwise. The bits of the root node are all 1. Furthermore, the bitmaps can be used to represent the occurrences of vertices in a tree, and they can be compressed. Next, we introduce the instant query algorithm. It returns the top k geotextual objects with the minimal scores. With the help of the R2T index introduced in previous, the query can be efficiently handled. The basic idea of IQA is to progressively return the vertices with the minimal score among all reverse two-hop labels. The active node is the node whose represented string, keywords edit distance to q, st or is not larger than to. It first compute active nodes in the complete tree. Then IQA finds the vertex with the minimal score for each reverse two-hop label of V in two-hop label of Q, where Q is the query vertex. It repeatedly selects the vertex with the minimal score among all reverse two-hop labels. In addition, IQA computes the minimal score vertex for each reverse two-hop label for initialization. To improve the efficiency, we can first compute the lower bound of the score for a reverse two-hop label. We need to only compute the minimal score vertex for father active nodes. Then, we design instant update algorithm. It update the query results when the query string changes, and handle changes incrementally instead of starting from scratch. There are 3 cases of string updating: inserting character s at the end, deleting character s at the end, inserting, deleting character s at random position of the query string. To tackle their cases, we design state rollback mechanism and query information inheritance mechanism. During the query, the state corresponding to each input letter is recorded. IUA rolled back to the state corresponding to the letter before the insertion or deletion. Then, IUA used the information rolled back instead of starting from scratch. The new query result is obtained according to the letter after changing the position. Next, we present experimental results for our proposed index and algorithms. In experiments, we use 8 real-world road networks. The table shows the details, and we use 5 methods as baselines. We show evaluation of instant query algorithm. IQA can be more than or equal to an order of magnitude faster than the comparison methods under different parameters. Next is evaluation of instant update algorithm. IUA can better handle the case of changing query string. IUA can be at most an order of magnitude faster than IQA because it incrementally updates the results. We show the index evaluation. R2T shows good indexing performance on all datasets. The maintenance of R2T is very efficient. To conclude, in this work, we study the problem of instant error-tolerant spatial keyword queries on road networks. To efficiently answer the queries, we propose a new index called R2T. Based on R2T, we present a suite of algorithms to answer the queries. Both theoretical analysis and empirical evaluation demonstrate the efficiency of our proposed index and algorithms. Thanks.